thinking a little bit differently about sensors in this session. So we're thinking events, we're thinking thermal, we're thinking outside the box. It's going to be really fun. I'm going to share a quick observation before we get started, which is that yesterday we had a dramatic drop in audience questions after lunch. So my request is that you stay awake, stay engaged. We only get one ICCP a year. So with that, kicking off this session, we have Mingxuan Kai from Berkeley. He's going to tell us how to use event cameras to do audio sensing.
Okay, thank you, Emma. So, hello everyone. My name is Mingxuan from Audio, which was co-led with my amazing lab mate Dekel. Microphones are widely used to record sounds. When an audio source, such as a speaker, plays an audio, we will always expect to record audio faithfully. However, when there exist multiple audio sources, the microphone can only hear the mixture of both audios. This could cause some problems when you want to hear each audio separately. Even worse, microphones are easily affected by unwanted sounds. For example, when we speak in a noisy environment, our voice can be covered by background noise. Or when we speak in an empty room, our speech is often overlapped with echoes bouncing off the walls. However, an interesting fact that many people may ignore is that the sound is generated from the vibration of the object. So what if we can use a camera to see those tiny vibrations? And then we can record vibrations from each audio separately, and then recover the corresponding audios from those tiny vibrations. However, imaging such vibrations will pose two major challenges. First, those vibrations generally have very low amplitude, which is difficult to see even for nearby objects. For example, in a lab video, the vibration from a tuning fork can only be seen clearly after it is magnified. Second, the frequency of vibrations that encode human speech information are generally too high for a standard camera to see, not to mention our human visual systems. To solve these problems, existing optical vibration methods can be categorized into passive and active sensing. In passive sensing, high-speed cameras with powerful zoom lenses are used to imaging the small vibrating area of the object. The setup can be relatively simple, but it struggles in capturing vibrations in high frequencies, which leads to low-quality audio reconstruction. You can also think about doing passive sensing with a high-speed camera, like capturing and sifting through oceans of information for tiny audio useful information. This is not only inefficient, but also extremely slow. The active sensing, however, uses an active laser source to illuminate the object, creating a very sensitive interference pattern to speckle, which directly encodes the vibration information into a speckle motion, leading to the high quality and efficient vibration sensing. But the image system is much more complex, together with complicated optical alignments. So in our paper, we propose an event-based vibration sensing system for imaging such tiny vibrations with an event camera. Our method realized high-quality audio recovery using active speckle sensing, matching some established benchmarks. More importantly, it features a simple hardware with event-based data acquisition and fast processing, approaching real-time reconstruction for audio recovery. So event camera is a very special type of camera which only records brightness change asynchronously. In the right video at the bottom, you can see only the moving hand is captured by the event camera, compared to the lab video taken by the standard camera. But why we want to use event camera? Oops. Sorry. Let's see. So let me continue. But why we want to use event camera for active sensing? So first, compared to standard cameras, event cameras have ultra low latency, allowing them to capture fast-moving objects like the tiny vibrations that encode human speech information. They can also be adapted to have very low bandwidth for fast data processing. And more importantly, event camera shows a unique ability to extract 2D speckle motion in a more natural way. For example, some early studies used fast 1D line-based camera to capture fast and high-frequency speckle movements, but the reconstruction quality degrades when the shift direction is not aligned with the sensor direction. To address this issue, a recent study proposed a brilliant idea to exploit the speed of a 1D rolling shutter camera and preserve 2D sensing ability of the global shutter camera by combining these two together. Oops. Oh. Sorry. Is there any issue?
Yeah. Let's take this out.
Okay. Is this one?
Yeah.
Okay.
You can take it from the front.
Okay. Let me continue. So this brilliant idea, trying to combine these two cameras together, but however, this dual shutter camera system needs to use a cylindrical lens and some delay optics to project the speckle onto the columns of the sensor, making the system very complex and difficult to align. The event camera, however, naturally has the ability to plane fast motions in 2D without using additional hardware, making it an ideal motion sensing device for vibrometry. Based on this consideration, we can just have an event camera and a single lens in our image system, but still preserve 2D sensing ability for high-frequency vibrations. And to sense these tiny vibrations, we illuminate the object, vibrating surface with a laser. And then we can capture the defocused speckle pattern using the event camera. When audio is generated, it causes the surface of the object to vibrate. So then, the surface vibration is encoded into a lateral shift of the speckle on the image plane. And here, we assume the vibration is within the memory effect range of the object surface, so the speck shift remains consistent and global across the whole field of view. In the raw data recorded by event camera, you can clearly see these speckle movements, which encode the vibration information. After the data collection, you can get the events of a speckle motion at each time point. And in this figure, the yellow curve shows the motion trajectory of the speckle, while the right triangle indicates its current position at T1. We can also see events at later T2, showing how speckle moves to a different position on the trajectory. We then apply the optical flow algorithm to estimate the 2D global motion between them. Next, when the speckle moves to the upper area, we can also estimate the relatively global motion again, and later repeat this process for the entire data. Once we compute the 2D flows that represents a speckle motion for entire data, we can extract the flow vectors at each time point. But since we are mainly interested in the magnitude, not the direction of the flow, so we align the x and y motions over time, find the dominant, like the vibration directions, and then project everything onto a single 1D axis. Because the flow represents a gradient of the original audio signal, we then integrate it to recover the audio. And finally, we apply some denoising algorithms to clean up the result. So this gives us the recovered audio waveform together with a spectrogram where the x-axis represents the time and the y-axis shows the frequency. And we will use this to show the audio result later. So now, I'd like to share some interesting experiments where we recover audios from those tiny vibrations using the method I introduced above. So in this first experiment, we try to record the vibrations of a speaker membrane when playing audios. So here, we have two speakers at the bottom of the left figure playing different audios at the same time. While the microphone records a mixture of both speakers, our audio system captures the vibration from each speaker separately by projecting speckles onto different parts of the event sensor. So then, we can recover the audio from the recorded vibrations from the left speaker and from the right speaker separately. We also record the indirect vibration of a chipback reacting to a nearby sound source and compare our results to some recent vibrometry method. So for example, Howard achieved a real-time audio recovery also by using event camera, but his method relies on passive sensing, and the algorithm is only used some zero crossings of events, resulting in some low-quality reconstructions. And Shannon, on the other hand, used the active sensing with a dual shutter camera setup. So this provides them with very high quality results, but they also required a time-consuming optimization process to merge different frames from two cameras, taking around 50 minutes to recover the same audio clip. In contrast, our approach combines the speed of event-based sensing with the quality of active sensing, achieving results comparable to Shannon's, but further reconstructed in real time. So now, let me play the audios for you to hear the difference. This is input speech.
Mary had a little lamb whose fleece was white as snow.
And this is a result using passive event camera. And this is a result using active dual shutter camera.
Mary had a little lamb whose fleece was white as snow.
So finally, this is our recovery.
Mary had a little lamb whose fleece was white as snow.
And to note, we reconstruct audio in real time. And finally, I'd like to show another interesting example to recover the audio during environmental distortions with vibrometry. So specifically, we want to recover the underwater audio with our vibrometry system. So as you may know, underwater sound often gets attenuated and even distorted as it travels through the water, making remote audio speech recovery a very challenging task. So here, we want to measure the vibration directly before it is propagating through the water. And in our proof of concept experiment, we had a waterproof speaker inside a box filled with water. To avoid the speaker from floating, we placed it inside a smaller water-filled box and anchored it at the bottom. When we record audio directly with a microphone from outside of the speaker or outside the box, the quality often degrades and it can become very faint and even hard to hear. So what we can hear is only the background noise. We then shoot a laser at the membrane of the waterproof speaker and use our system to capture its vibrations and recover the audio even if it is underwater. It is not perfect, obviously, but still shows superior quality than the direct microphone recordings. So in summary, we try to develop an event-based vibrometry system that features high-quality audio recovery with simple hardware and fast processing. We also showcase some interesting examples of vibrometry over traditional microphone recordings. And please scan the QR code to see more details and examples on our website. Our code and data are also available on GitHub. And at last, I'd like to thank all members from World Lab and our reviewers for sharing their wisdom on our paper. Thank you so much for your attention.
After lunch question, we've got to have someone with a microphone.
Mentioned that the 2D flow is projected onto 1D before integration. So how does this projection work, and is there any risk of losing some frequency components in this process?
Yeah, I think that's a very good question. So actually, now we just do the very simple process. We just take the magnitude and project it into 1D. Because first, also explore trying to project different frequencies along different axes. I think this is more. I think this would be a better way to try to construct this kind of signal. But now in this paper, we only try to explore the simplest way. Yeah.
Okay, thank you so much.
Hi, thanks for the talk. I'd like to ask you information regarding. And sorry, what's the optical flow that you use, and what's the maximum frequency you can actually detect using this method?
Yeah, thank you for your question. Yeah, actually we use two optical flows. First is totally based on the synchronous, based on single events. And we also apply the frame-based method, which is, I think, Galor this kind of traditional optical flow algorithms. We prove that both of the single algorithms can work. Of course, if you can come up with a better optical algorithm, it will give you better results. And for the highest frequency, we test the chip signal the chip signals, which from 0 to 10,000. And in our system, in current setup, we can ship around 5,000 hertz frequencies in frequency. Yeah.
Excellent. We'll take one last question.
Yeah, really interesting project. I was wondering what sets, like, how many different sound streams can you disentangle from the speaker? Like, what sets that limit?
Yeah.
And what about your spectral resolution with which you can disentangle this stuff?
Yeah. Thank you. I think this is a very good question. So actually, so first we assume all the audio sources are physically separable. So that we can point our little source into different audio sources and then reconstruct them separately. And because we want to project the speckles onto different parts of the sensor, so the maximum number we can recover depends on the sensor size. We cannot do unlimited numbers. And now we tried two different audio sources. We also tried 3 different audio sources. Of course, we can do more, but there's the upper bound for that. Yeah. Also for the spectrum resolution, we tested that in our paper. We now can achieve like less than 1 hertz spectral resolution. Yeah. Probably this isn't enough for like speech applications, but probably we can do better in that case. Yeah.
All right, let's thank Mingxuan again. Up next, we're going to be hearing from Connor Hashemi. He's going to be presenting our Best Paper Award winner on how to use event cameras to centroid point-like objects.
So hello everyone, my name's Connor. I'll be presenting our work at Kitware on centroiding point objects with event cameras. An important 2 years ago at the ICCP Doctoral Consortium in Madison. So very appreciative of the community here. So a quick overview of our goal, which is to localize objects in a 2-dimensional image that are too small or fast to have discernible features. And this is useful for a variety of areas, such as projectile tracking, space situational awareness, and star tracking. So using conventional framing cameras, there's currently some limitations. The first is that fast objects, such as projectiles, often appear as blurs on the framing camera due to the finite exposure time of the sensor, and therefore there's uncertainty in the centroid estimation. Also, since these objects are small, there's a lot of empty and background pixels that are wasting processing power. And conventional cameras can often suffer to have the dynamic range necessary to image bright and dim unresolved targets in the same image. So this led us to utilizing event-based sensors for centroiding, where event-based sensors trigger events based on whether the intensity changes by a thresholded amount. And the biggest advantage of these sensors is their low latency. So if we see this image frame of an object, of a blurred object, the corresponding event frame, you can more clearly see where the centroid would be located. Additionally, since events only trigger when something happens, there's less wasted energy in background pixels, and they have typically a higher dynamic range. So because of this, event-based sensors are well fit for centroiding. However, there are some unique challenges in implementing old centroiding techniques for intensity images on these new event-based domain. The biggest reason is the non-Gaussian distribution of the positive and negative events, where we have this so-called bow shock of positive events and a long negative event tail. And this is a problem because many of the previous centroiding techniques really assume an ideal Gaussian intensity distribution of the object, which this clearly is not. This is further complicated by the fact that this distribution seems to change based on the intensity and velocity of the object. As an example here, we have 3 different objects with 3 different apparent centroid locations relative to the events. And this is a problem because this suggests that your centroiding technique needs to change based on the object you are imaging. So our goal is to develop a new technique that's particular for event-based sensors. And a key insight to doing this is understanding that because this event distribution changes based on the object parameters, we can actually utilize this as an advantage because it should contain more information than a normal intensity distribution of an unresolved object. So our goal is to create a new centroiding algorithm where we're going to utilize spatial cues in the event distribution to not only estimate the unresolved object's centroid, but also its velocity. And we're going to do this in very small time samples or time batches of 5 milliseconds to best utilize the low latency aspect of event cameras. So first I'll be going over a quick model of the event distribution to gain insights before describing how we created a data set and trained a model on this data set. And finally, I'll evaluate the centroiding performance against other models and theoretical bounds. So first, to understand the event distribution, we utilize the event likelihood, which describes the likelihood of an event occurring at a pixel x and at a point in time t. And typically, this is derived as the partial derivative with respect to time of the log of the object's intensity at that pixel. So what this means, if we have an unresolved Gaussian object moving to the right, we would get these distributions shown here, which essentially boil down to the spatial derivative in the direction of travel. What's important to note is that these distributions only change as a function of position, which does not correspond to what we observe in real-life experiments. So to account for this, we utilize a more physically accurate model of the event likelihood, where we include the pixel's low-pass cutoff frequency, FC, which is a function of the object's intensity, and we also include the current pixel's voltage. Now, because we include the current pixel's voltage, this is actually a much more difficult equation to solve. But if we assume that the object is very dim, it has a Gaussian distribution, and it's moving at a constant velocity, and these are all normal assumptions, or relatively normal assumptions for unresolved object imaging, then we can obtain a closed form solution. And this solution is shown here, where we can see many different likelihoods which change based on the intensity and velocity of the object of interest. And this corresponds more to what we see in our real-life experiments, where all these variables are coupled together. So while we can show that they are coupled together, it is still unclear how we can use this for centroiding or what information is useful. So to do that, we have coupled insights via Kramer-Rao bounds, or CRB for short. And in this presentation, it's just important to remember that a lower CRB means that the distribution contains more information about the unknown object parameters, such as its centroid or intensity. Speaking of intensity, we're actually going to keep it constant because typically when we're tracking these unresolved objects, they're changing their velocity and position and not so much changing their intensity. So the first insight is looking at the centroiding location and the Kramer-Rao bound. And we notice that when you utilize just the spatial information, it is almost as good as utilizing the spatial and temporal information, which suggests that the spatial features are what hold the majority of the information, not the temporal features. And again, this is really just because we're having a very small time sample of 5 milliseconds to analyze these events. If you have a longer time batch of seconds or minutes, temporal information becomes more important. The other interesting thing we notice is looking at if we can estimate the speed, or the speed estimation Kramer-Rao bounds. And when we look at the positive and negative events, typically negative events were not very useful in estimating the location of the object, but we noticed that they had significant amount of information in estimating the velocity or speed. And so this is a useful observation because typically in these centroiding algorithms, people disregard the negative events due to their high entropy and seemingly not very useful in helping us determine location. So with these insights, our goals are to train a data-driven model to focus on the spatial features of the distribution. And we're going to look at positive and negative events together and not only estimate the centroid, but also the velocity. So now we come to how we collect this data set to train our model. So we have a Prophecy EVK4 event camera focused on a high frame rate monitor, where we put 7 Gaussian dots on the monitor, move them to the left for 1.5 seconds, reset them, randomly change their size, intensity, and velocity in doing so, and repeat. So here is a quick video where on the left is our monitor video, so what's being shown on the monitor, and on the right are the captured events, where white is the positive events, where you can see that bow shock effect, and blue are the negative events, where you can start seeing the negative event tails. So when we do this for over 3 hours, we can obtain 2 million unique 5 millisecond event streams, which is ample to train our model in. So for model training architecture, we settled on a 3-layer LSTM network. And the reason we use an LSTM instead of a CNN, which would be typically used to extract spatial information, is that we found the LSTM to not only perform better with the sparse event streams, but also allows us to do an ablation study that we'll show later on. So to train the model, we take the events polarities timestamps, randomly rotate and translate them before feeding them through an LSTM model. And at the end, we read out the centroid speed and angular heading of the object. So now we come to results. So here are just a few examples to gain some intuition on the different sets of objects we are trying to centroid. And here is a result on a test data set we captured. So here we're comparing it to non-data driven methods such as the mean centroid, intensity reconstruction, and Gaussian maximum likelihood. Our model, shown here on the bottom, has a centroiding error of just under a pixel, which is about twice as good as the next best model. However, what's more impressive is looking at the speed error, which is 18%. And this is over 5 times more accurate than the next best model. And this highlights the uniqueness of our approach in that we can extract more information from this event distribution than you could normally do with intensity centroiding algorithms. With our LSTM, we can also perform an ablation study where we retrain the network with different information to see how the error metrics change. So when we remove the event order or remove the timestamp information, we notice that we have minimal effect on our resulting test metrics. And this agrees with our initial hypothesis and CRB analysis that this temporal information has very minimal effect in these 5 millisecond time batches. Additionally, if we remove negative events, we retain the same location accuracy but get worse speed estimation, which suggests that the positive events are useful for location, while speed or negative events are more useful for velocity. And we get the vice versa when we remove the positive events, where we get very poor location estimation and better speed estimation. So this is agreeing with our initial hypothesis on CRB analysis in the beginning. And so finally, I want to briefly talk about empirical Kramer-Rao bounds. So with our captured data sets, we can actually look and be able to accurately estimate what the theoretical limits of this centroiding precision. And this is important because in many applications, such as star tracking, where there are important bounds to have on centroiding, there currently is nothing out there for event-based centroiding. So here we're able to show the Kramer-Rao bounds and our model's performance relative to them. And we can see that they have similar shapes, but there is still some gaps that we can have some improvement, especially in the centroid estimation. So finally, just in terms of summary, our goal was to leverage the event distribution for unresolved object imaging, or unresolved object centroiding, and we really focus on small time batches of 5 milliseconds. We demonstrated that the spatial distribution of these events is proportional to the speed, intensity, and location of the unresolved objects. And then finally, we showed that utilizing just 5 milliseconds of events, which is about 48 events on average, our LCM was able to localize object within a pixel and velocity within 17 to 18%. And we also showed empirical Kramer-Rao bounds. And the paper includes more results, which includes further analysis on 20 millisecond time batches, so it's increasing the amount of time we're analyzing, more ablation studies on what information is useful, and we also perform on a public star tracking data set that we captured. So thank you, and here's the GitLab.
Thank you, Connor. Any questions?
Hi, thank you so much for the great talk. I was wondering whether this method would be applicable if you're tracking something that's not a star or is not, maybe is like ellipsoidal or like more irregularly shaped.
Yeah, that's a good question. I think a lot of the underlying math will work out similarly. So it still will depend on the speed, position, intensity, these distributions. So you do have to have something that's more careful. With our data set capture, we did assume that the object is Gaussian because that is a common assumption, but I think it can be adjusted for different size objects. But either more data will have to be collected or a different physical model will have to be implemented.
See a question from Sarah.
Thanks for the great talk. My question is kind of similar, but I'm just curious about this bow shock like curvature in the front. Is that because the object is round, or is there some other source for that shape?
Yeah, there's a couple reasons for it. So one of the reasons when we've been looking at it, I mean, a naive reason is that it's a Gaussian, so you have a derivative of Gaussian. It's going to have that round thing as you're talking about. The other reason is that when we look at the model of the pixel here, we have this low pass cutoff frequency that is changing as a function of intensity. So when you have this bright object that's entering, it's changing a lot. And then there's this logarithmic photoreceptor also that's impacting things. So it is a more complicated phenomenon than just circle, but circle is a big reason.
All right, I have a question actually. You mentioned briefly that there was this qualitative change in the kind of information that was useful to you as you changed timescales. Mm-hmm. Can you give us a little more intuition around that?
Yeah, so we focused on very small time batches, again, to utilize the low latency aspect of event cameras, but also to show the spatial information encodes the majority of the information. But as you include longer and longer time batches, you can obtain better metrics, and this makes sense. You get better SNR, but also the temporal information starts mattering more and more. So here's an ablation study we have about time batches, where you can see location, speed, and angle kind of start to drop off, and eventually we get to a asymptote at around 0.8 location error. So yeah, I think different models, if you want to have longer time batches, different models besides LSTMs might be more useful, something with more memory, or maybe go to a CNN in that case.
Thank you. Let's all thank Connor again. All right, we are now going to switch from events to thermal cameras. And kicking us off, we have Kazuma Kitazawa, who will be telling us about shape from polarization in thermal emissivity and reflection.
Okay, thank you for the introduction. My name is Kazuma Kitazawa. I'm a master's student at the University of Tsukuba in Japan. About shape from polarization of thermal emission and reflection. Our goal is to capture the 3D shape of challenging object, such as transparent or very dark object. As you know, existing methods often struggle here. Thermal imaging lets us avoid these problems. In the thermal infrared spectrum, most materials are opaque, uniform, and emissive. These characteristics are ideal for photometry, so this raises a fascinating question. Can we use thermal imaging for high-quality 3D reconstruction? In recent years, several studies have explored this question. They have utilized different cues, such as shading, attenuation in the air, and temporal heat conduction. But these methods have several drawbacks. In contrast, we focus on an underexplored modality, the polarization of thermal infrared. By leveraging this polarization cue, we can achieve fast, passive, and detailed shape reconstruction. So what is our approach? Our method relies on the principle of shape from polarization. Shape from polarization, or SFP, is a technique to estimate the orientation of the surface normal based on the polarization state of the light emitted from the surface. It has been studied for many years in visible light spectrum. There are two challenges in applying SFP in the thermal infrared spectrum. The first is the polarization model. In the thermal infrared spectrum, surfaces not only reflect light, but also emit light. We need to consider both phenomena. And the second is the sensing model. Imaging of thermal polarization suffers from several unique errors that need to be carefully corrected. While prior work on thermal SFP does exist, but it has overlooked these key challenges. As a result, they reported large errors, which might explain why this modality has been underexplored. By tackling these challenges, we unlock the true potential of thermal SFP and achieve high accuracy normal estimation. First, let's look at the polarization model. What's actually happening at the surface? Emission light originates from within the object. As it reaches the surface, it is refracted and emitted outwards. So emitted light is polarized according to the Fresnel's equation for transmission. Prior work of thermal SFP only considers this emissive component, but this model is incomplete. In reality, we can't ignore reflection because everything around the object is also emissive, and this environment light is reflected by the target object surface. So the observed light is a combination of polarized emission and reflection, and its polarization state can be related to the surface orientation. Since the polarization angle of emission and reflection are orthogonal, they partially cancel each other out. This reduces the degree of polarization. In particular, when there is no temperature difference between the object and its surroundings, the degree of polarization becomes almost zero. This raises a major constraint, requirements for thermal contrast. Conversely, if there is thermal contrast, we can obtain the shape information through the polarization state, and based on this model, we can reconstruct the shape of the object. We can estimate normals directly from this model, but some challenges remain. For instance, an ambiguity in the azimuth angle can lead to incorrect estimation, especially in concave regions. Furthermore, complex phenomena like interreflection do not follow our model. To robustly handle this effect, we employ a neural network. The network is trained on a purely synthetic dataset, which is generated using a physics-based polarization renderer. This approach provides robustness while remaining faithful to the physical model. Next, let's move on to the sensing model. The imaging system consists of a camera and a polarizer, just as in the visible spectrum. However, the quality of the raw image is degraded by 3 errors unique to thermal polarization. The first is the sensor's fixed pattern noise. You can see it as this stripe-like pattern here. The second is the light from the polarizer. The polarizer's own emission and reflection are also significant sources of error. And the third is the attenuation at the sensor's surface. Curiously, the microstructure on the sensor's surface attenuates specific polarization components. We formulate the image by taking this effect into account. The light from the scene is represented by the Stokes vector, and the properties of polarizer and sensor's surface are represented by the mirror matrix. Using this equation, the polarization state of the scene light can be calculated from images captured with a rotating polarizer. However, these offset components are difficult to calibrate. Therefore, we use a black body shutter to calibrate this offset at capture time. First, the camera captures the scene with rotating polarizer. Then we close the shutter and capture it for calibration. Thanks to this, we can finally capture reliable images of thermal polarization. We implemented this imaging system and created the thermopole dataset. To our knowledge, this is the first real-world dataset for thermal infrared SFP. It consists of objects with various shapes and materials. We use this dataset to evaluate our method. First, let's look at the polarization images. Here is a comparison with visible light spectrum. In the visible spectrum, polarization is strongly affected by transmission or albedo. This makes it difficult to reconstruct shape based on polarization. In contrast, look at the thermal images. You can see a clear correspondence between the shape and polarization state. This shows the power of the thermal polarization for 3D shape recovery. Next, let's look at the results. Here are the estimated normal maps for a transparent object and a black object. Both are challenging for visible light methods. In the visible light images, the shape is barely visible because of the complex refraction or the lack of reflection. However, in the thermal infrared, they are easy targets. Our method successfully reconstructs fine detailed normal maps. On the thermopole dataset, we achieved an average MAE of 10.3 degree. We can't compare this result directly with thermal light SFP methods, but the metrics are on the same level as state-of-the-art methods, while our dataset includes a number of challenging objects. Our method can also handle various materials. These spheres are made of different materials, such as glass, acrylic, phenolic, wood, and stone. They are transparent or textured. These materials look completely different in visible spectrum, but in the thermal infrared spectrum, they have similar property. As a result, it is easy to estimate their normals. And here's a task that was nearly impossible before, capturing the shape of melting ice. It's transparent, it's deforming, and active methods cannot be used because they would affect the melting process. Our method makes it possible to capture the deformation of transparent ice in a completely passive way from a single point of view. It might be possible to capture the shape of more dynamic subjects, such as liquid, in the future. In conclusion, we propose the shape-from polarization method in the thermal infrared spectrum. Our method accounts for both emission and reflection, and also addresses the errors in the imaging system. The surface normals are robustly estimated by a physically grounded neural network. Through our experiments, we have demonstrated that our method can handle a wide variety of shapes and materials. However, some limitations exist. First, our method requires thermal contrast between the object and the surroundings. This means the object needs to be either warmer or cooler than its surroundings. Additionally, it is difficult to handle certain materials, such as metals and rough surfaces. Nevertheless, we believe that our work shows a promising direction for shape measurement. Thank you for your attention.
Thank you, Kazuma. Any questions? You have to do that calibration, and why?
Okay, we capture multiple images with a rotating polarizer for the steam capture. And after that, we have to capture the black body for calibration. So we have to capture the black body object once for each capture.
Thank you.
Yeah, really nice work. I have one question. Here, like, you're capturing the long wavelengths infrared, and mainly you're capturing basically long wavelengths infrared of light.
Yes.
And I would guess, like, because the main signal for the shapeform polarization is the light coming from inside after a lot of subsurface scattering, or when the light comes out of the interface, then you have your Fresnel refraction, then you estimate the surface normal from that one. And I'm wondering, like, if you have such long wavelengths of light, likely you're going to have a lot of, like, some of the light may come out of the different places from the surface. Like, for example, if we use the longer wavelengths, then we usually expect to see a lot of subsurface scattering. And I'm wondering, like, have you observed this impact of using the longer wavelengths on the estimated surface normal's frequency? Can you resolve this high frequency of the surface normals using this long wavelengths infrared signal? Do you have any clue on that?
In the thermal infrared spectrum, we can ignore the subsurface scattering because light is attenuated by the medium of the object. So we only consider the specular reflection and emission.
Okay, yeah, sounds good.
Thank you.
All right, let's thank Kazuma again. Next, we're going to hear from Akihiko Oharazawa from CMU, who will be sharing a really lovely combination of thermal imaging with shape from shading.
Thank you, Emma. Hello, my name is Akihiko Oharazawa. I'm a visiting scholar at Carnegie Mellon University. Today we present our work in heat conduction and shading. So shape from shading has been a long-standing problem in computer vision over the 40 years. There are rich history behind, and many amazing work has been done. And the main challenge is that how to deal with its ambiguities. For example, when the case of multiple images with known lighting, Robert Woodham proposed photometric stereo in 1980s, which shows that the surface normal and albedo can be estimated under the three known image lightings. And however, this requires at least 3 images correspond to the known lighting. So what happens when the lighting is unknown? In that case, an ambiguity arises. Shape, albedo, and lighting can be estimated up to 3 degrees of freedom. This is known as bas-relief ambiguity. So how about known lighting with single image? By considering the Lambertian surface, shading term eta is a dot product of surface normal n and lighting direction s. When the lighting direction s is known, eta satisfies along the cone. So which means the infinite number of possibilities of normal lie along this cone. When the lighting direction is unknown, in that case, ambiguity becomes worse. So shape from shading typically requires smoothness or known boundary or strong prior to deal with ambiguities. So recently, deep learning approaches has been proposed, however, does not guarantee to resolve the ambiguity. So here, we aim to contribute theoretical aspect by addressing the fundamental question, how can shape ambiguities be resolved? So let's take a look at shading carefully. In physics, shading is proportional to the absorbed light. And absorbed light becomes heat. So this means the shading involves the light transport and heat transport. And heat can happen through one of three modes, namely convection, radiation, and conduction. And importantly, heat conduction is shape dependent. So recently, shape from heat conduction has been proposed. By observing the heat conduction and fit the heat transport equation, allow us to extract the Laplacian, which is the intrinsic property of the shape by comparing to the extrinsic properties such as normal or depth. Laplacian described as mesh edge length and encoded the shape information. So however, this method requires 2 to 4 thermal videos to resolve the ambiguity. Because shape reconstruction from Laplacian also suffers from the ambiguity. When the Laplacian constrained to the lie along the camera rays, the ambiguity becomes binary, concave or convex. This means the flipping no-local shape provides the same Laplacian value. So shading has cone ambiguity per pixel, and Laplacian has also has the ambiguity, binary, concave, convex ambiguity. And importantly, Laplacian preserves the local curvature. So what if we can collect this binary ambiguity? Our key insight is that by combining the Laplacian and shading, so Laplacian provides the concave or convex with different surface normal. Now, let us assume the lighting direction is known. Shape from shading gives you a cone per pixel. And only one satisfies both the Laplacian and cone constraint, which allow us to identify the unique solution. Then, how to mathematically formulate this idea? To compute the normal from Laplacian, we use the regular grid 6 neighboring edges. Laplacian can be computed as cotangent weight Wij, and then we derive the Laplacian closed form as surface gradient P and Q. So this allows us to compute the Laplacian weight Wij as PQ form. So here, our equation shows that the Laplacian remains the same when the surface gradient PQ and replaced by its negative value. So this is exactly what the local binary ambiguity is. Now let's see what happens in the shading. So Laplacian allows both positive and negative PQ values, and the shading equations be written as follows. Then plugging into the both PQ value to the shading equation, we obtain different shading term eta. So which means we can resolve the ambiguity by computing the resulting shading term eta. And we should note that our theory cannot resolve the ambiguity in two special cases. First one is frontal parallel lighting. In this case, the lighting becomes 0, so the ambiguity cannot be resolved. And the second case is specific surface orientations. When the local binary normal lie along the line equidistant from the lighting, the ambiguity remains unresolved as well. So without these cases, our theory is applicable to almost all scenarios. And one advantage of the Laplacian is light independent. As shading equation has source term, shading is dependent on the light. On the other hand, our equation for Laplacian does not have source term, since the Laplacian is the intrinsic properties. This implies that if somehow we estimate the source from Laplacian, we don't need the light assumption. So this motivates us to estimate the lighting from Laplacian and shading. We propose a 3-step process. First, we extract a near planar using the Laplacian. And second, collect the sign of the planar patches. And finally, we apply reverse photometric stereo which is a new concept of the estimated lighting. Let's take a look at each step. So here we start with the Laplacian as closed form PQ. Now let us assume that PQ are the same for all edges. So this allows us to approximation the neighboring pixel are the same normals. Then all 6 edges described in PQ become 3 equations. By solving this equation, we can compute the PQ value. However, we don't know the sign of the PQ value. To disambiguate the sign, we define subset F, and then find sign that's consistent with the shading term eta. Then we get the correct sign. We get the estimated PQ value. By using the estimated PQ value, we estimate the lighting. Here we introduce a new concept of the reverse photometric stereo. We have estimated PQ value and known shading term eta, and unknown is lighting. Solving S by least squared estimation allow us to estimate the lighting. So here is the result that's showing the source estimation. By comparing to the ground truth, our method estimates the light source position less than 0.1 angular error for all objects. Now we have source direction. Then we estimate the surface normal in terms of shape. One naive way is to estimate the PQ, which gives us the 2 degrees of freedom. But in reality, we only need to search along the cone. So we introduce the T parameterization. So this is 1 degree of freedom because shading value, eta, lie along this cone. So this is the minimum expression to search the shape. Then we defined our objective function for T. Here, objective function has only Laplacian error, meaning we don't need to introduce any prior, such as smoothness. So this because the Laplacian is actually smoothness itself, what we needed. Since our approach resolved the ambiguity step by step, we only optimize the T for entire pixel. So here showing the result, that's shape reconstruction for shape from shading and shape from Laplacian without any constraint. And you might thought, why do we not to jointly estimate the shape, both shape and lighting? In fact, joint estimate strategy without priors suffers from the local minima, making shape recovery fails. In contrast, our method, shape from Laplacian and shading, can estimate the shape closely to the ground truth. Error computed by using mesh route, object has been scaled and aligned. Per pixel differences has been computed. So here is another result. Shape from shading, shape from Laplacian, and joint optimization fails to recover the shape. On the other hand, our method estimates the concave or convex shape collectively. So here is another result. And also as a result as well. And to assess the robustness to noise, we tested add noise to input shading and Laplacian. Our method shows that still a reasonable reconstructed shape as like this. And we also simulated noisy thermal videos with Gaussian plus fixed pattern noise. We extract the Laplacian from thermal frames and then applied our method. Some region fails, yet overall we can estimate the shape. And finally, we analyze the method in the presence of complex BRDF with intersection scenario. Our approach produces slightly shallower shapes, yet overall reasonable result. However, this suggests that when the interreflection dominates, shading model can result in larger errors. This should be interesting perspective in the future work. To conclude, we show that both Laplacian and shading suffers from the shape ambiguity. And we also showed that Laplace shape ambiguity can be theoretically resolved by combining the Laplacian and shading, even in the severe case when the lighting is unknown. Thank you for your attention.
We have time for one question for Akihiko. I have one. So you have this really nice, small, well-characterized set of remaining ambiguities. And it seems like a lot of those you could mitigate in practice. Could you just go back and tell us a little bit more about that?
You mean about the constraint?
Yeah, the sort of, there's a few situations where you say you would fail.
Okay.
And it seems like some of those are kind of point-wise, sparse occurrences.
Let me see. So here's an exception case. So mostly our case is there is no case like such entire pixel has the case too, such as specific orientation. So there are so many the less cases like entire pixel is in the case too. So most cases we can recover the shape entirely. And we also applied using the propagation strategy, starting with 1 point and propagate the entire pixel. So in that case, the case 2 can be eliminated.
All right, thank you. We can discuss more in our coffee break until 5. Let's thank all of our speakers again.